This is a Goodfellas production.
Ah, no, lads, seriously.
Does size really matter? In evolution, I mean.
And why do some species grow so big and others stay so small?
And does Cope's rule really apply to all of those species out there?
Does the rate of growth change throughout evolution?
We need to look at this more closely.
Some of the largest creatures on Earth were the sauropods. Sauropods were hugely successful and lived from the late Triassic and diversified up until the Paleocene extinction. They were very specialized dinosaurs and had no limit for food sources because they were so large. The Argentinosaurus, for example, was between 30 to 35 meters long and weighed between 80 to 100 metric tons. Their bodies grew so large firstly because they possessed an internal body skeleton. Their bones were slightly hollowed, which allowed them to grow so big. They had long necks, long tails, short pillar-like legs, and small heads. To grow so big, metabolism needed to be slowed down. An avian-style respiratory system, special adapted digestive systems, and slow reproductive systems helped. Now to take a look at the largest mammals alive today, the blue whale. The blue whale weighs between 150 to 170 metric tons and are around 30 meters long. They are also heavier than 40 African elephants. Cetaceans have the highest rate of body inflation as they have fewer constraints, such as gravity. The buoyancy of water counteracts the force of gravity. Without the buoyancy of water, the whale would collapse under its own weight. So Cope's rule suggests that all organisms tend towards large sizes. After the mass extinction between the Cretaceous and the Paleocene, mammals were no bigger than the average house cat. They then evolved to creatures like the Ambulocetus, to the Basilosaurus, and today we have huge mammals like the blue whale, which we saw earlier. This proved Cope's rule, but there is some evidence to counter-argue the rule, like the Maniraptora evolving to smaller birds such as the Confuciusornis. Experiments to prove Cope's rule were looking for trends in directional growth for which there was no conclusive answer. They were also looking to find upper limits to which animals could grow. Sauropods showed no indication of just how big they could grow, while theropods and mammals like whales did show upper size limits. All this speculation and lack of concrete evidence has led to some belief that Cope's rule is an artifact. This may be the case because larger bones are more easily fossilized. Studies have shown that species such as avian dinosaurs shrink faster than they increase. There are two main reasons for this. As organisms get bigger, they run up against different design constraints. Dealing with these problems requires innovations, such as new genes and new ways of reading the development program. All mammals, regardless of their size, must grow from a single cell and go through a developmental phase when they are small. So to shrink, all they have to do is cease development early. An example of how long it takes for a species to grow big can be seen in the evolution of the elephants. 50 million years ago, they resembled pigs, had short legs, long bodies, and lived in marshy areas. Over 10 to 20 million years, generations of elephants increased in size, which specialized them to cope with the changing environment. As they grew taller, their lower jaw elongated to reach the ground to feed, and their snouts evolved to trunks which covered their lower jaw. The lower jaw proved tricky, so trunks were selected over these jaws. It helped them eat, drink, bathe, and lift. Nostrils migrated to the tip of the trunk. They could now begin to breathe while being submerged in water. In the last 150 years, it has been studied that elephants' tusks have decreased in size. This is suggested to be due to rates of evolution can be determined by gradual evolution versus punctuated equilibrium. Gradual evolution is the gradual change over a short period of time. Change is slow, constant, and consistent compared with punctuated equilibrium, which is a very rapid change. It often occurs through mutated genes of few individuals. Punctuated equilibrium can be caused by natural disasters or changes in the environment. An example of punctuated equilibrium can be seen on an island off the coast of Croatia. In 1971, 5 adult pairs of Italian wool lizards from a neighbouring island were moved as part of a research project. The change in environment caused the lizards to undergo large-scale and rapid evolutionary changes, such as changes in head size and shape, increased bite strength, and the development of a new structure of a digestive tract over a short period of 36 years. These changes in morphology occurred because they needed to adapt to new environments and food sources. These changes were because they were forced to eat plants instead of their usual food,
Okay, so
insects.
we've looked at all of the examples. So what can we pull from this then? Well, large animals are more specialised, so they've greater resources for feeding and they're less susceptible to predation.
Yeah, but they're generally found in small numbers due to their slow rates of reproduction. Does this leave them more vulnerable to extinction?
And smaller animals are less specialised and found in big numbers because of their fast reproduction.
So what's better to be then? Well, you can make a competition between specialisation and longevity.
So, is it better to be specialised and not live that long, or be unspecialised and outlive everything?
So success doesn't depend on size.
Yeah.
No need to worry, guys. Who's making tea?
Grania.
Okay.
No animals were harmed in the making of this movie.
Woo!